Hi, in this video, we want to take a look at multiplicative, seasonal, autoregressive, integrated moving average models. All right, that is a lot to spit out. All right, so what we're going to do is that we're going to take our time series and we're going to figure out our differencing on the time series. We're going to figure out any transformations we want in there. But we'd actually do that before we do our differencing. And we would figure out regular ordinary autoregressive, and we'd figure out regular ordinary moving average. While we're moving through this process, we're going to keep an eye out for the possibility that there is a seasonal component. Now, when we say seasonal, something about this is that we need to have subject matter knowledge of what potentially could be the time span of seasons. So if I was talking about, business cycles over a quarter, I have to know that it's going to be around, 91 days. Now, if I'm talking about something that very naturally would be yearly, then, we will be looking at maybe like 12 months on my data, depending on what's going on. So when we want to find the seasonal aspect, we need to have some kind of subject matter knowledge to know like where I should be looking to see where are going to be the degrees of the seasonal components. Now, why do we call this multiplicative? Well, let me show you why. If I come down here, all right, so I'm skipping ahead to definition 3.12. The reason why this is called multiplicative is that you can see that I've got, here's a seasonal autoregressive, regular autoregressive, I've got seasonal differencing, and I've got regular differencing, and these are all being multiplied by each other. Notice that these are these are operators on the backshift operator. Each of one of these components in this product is an operator on the backshift operator that operates on our time series, X. On the right-hand side, I have seasonal moving average component, and I have regular moving average component being multiplied together. And so this multiplication of operators on the backshift operator is where we get the multiplicative aspect of this. All right, so let's take a look at this. Let's start from the beginning. All right, so we're going to be working through 3.9 of time series analysis and its applications. Here are the authors' names. Here's our GitHub page, and you can download the textbook for free if you're a UCF student through the library. All right, so an important table for this. This is very similar to the one I showed before for regular autoregressive and regular moving average, that what we're going to do, using my subject matter knowledge of what a season should be, how long it should be, I'm going to look at my ACF. I'm going to look for a seasonal cutting off for ACF or a seasonal PACF cutting off to indicate if I should have a seasonal autoregressive component or maybe a seasonal moving average component. And the line of thinking is just like with regular autoregressive and moving average models, except we are looking at multiples of the season time span. So like 12 if we're dealing with yearly seasons and we have monthly data. And notice that if I have ARIMA, things lag off for both the ACF and the PACF. And so it's very similar to what we had before. All right, so now we can adjust our autoregressive moving average models to address seasonality and non-stationary behavior. Seasonality is when we have dependence on the past that is stronger at some multiples of a lag value. And so a good example of this would be 12 if I have monthly data and there is a yearly aspect to it. Monthly economic data tends to have components with a lag 12, while quarterly economic data tends to have a strong component of lag 4. All right. All right, so if I want to do a pure seasonal moving average model, and so here I'm going to have, so in our notation, I'm going to use capital phi to indicate that this is a seasonal autoregressive. So remember, lowercase phi is regular autoregressive, and the authors choose to put a subscript for the degree. And in this notation, the capitals refer to the degree of the seasonal aspect, and lowercase refers to the regular degrees. And so here, capital P gives me the degree of the seasonal autoregressive. Here I've got capital theta for seasonal moving average. And then that should be a capital Q. I messed up. So capital Q indicates the degree of the moving average. And you'll notice that we have the seasonal part here, which is also denoted here in the model structure. And so you'll notice that our operator is not working directly on the backshift operator. It's working on a power of the backshift operator. And that power is the seasonal aspect. All right, so a pure seasonal autoregressive operator, you'll notice that I've got exponents of multiples of S. And I've got P terms, right? And then for the moving average, it works out very similarly. Multiples of S all the way across. All right, so a pure seasonal ARIMA PQ with season S model is causal when the roots of the autoregressive part are outside the unit circle, and invertible when the roots of the moving average components are outside the unit circle. And notice that I have a power of Z for both of these. So this feels very similar. This is basically just approaching what we've done before with autoregressive and moving average the same way. Now we're just tacking on a part that, hey, we say only deal with powers of the seasonal aspect. All right, so let's go ahead and do a seasonal autoregressive series. And so let's do first order. And so, just the simplest one I could possibly do. So I've got backshift operator of power of 0. The textbook denotes as a 1. Usually I put b to the power of 0 there. Here's a coefficient. And now, since I'm talking about a year and we've got monthly data, I have b to the power of 12. All right, and so I get this as my process, just kind of written out. Now, if we sit down and work through this, this is very similar to the calculations of an autoregressive degree 1 process. And so this is a seasonal degree 1 autoregressive process. But if I sit down and start doing the pencil and paper math, it's really, really, really similar to the regular degree 1 autoregressive process. Okay, so let's go ahead and simulate an example like this. Oh, and something to notice is that in this particular situation, we have 0 covariance when we don't have multiples of 12. If I have multiples of 12, we have a very nice formula here to work this out. And the correlation is super, super clean. All right, so let's go ahead and run a simulation using R to work this out for us. So here, we're going to say 0.9 for the seasonal autoregressive part. Here, I'm saying the seasonal length is 12, and I want 37 as my number of points generated. And then we're going to shift everything by 50 because here we're not going to assume that we have a population mean of 0. All right, so let's go ahead and plot this out using my time series plots. And notice that I put type C here. And we're going to put down the month, letter of the month, as my character on the plot. All right, so here, January, February, March, April, May, and so on. And so here we can see the J's are, coming, relatively close to each other. We see February, and so we can see the seasonal aspect here very nicely. All right, so now let's go ahead and compute the ACF and PACF for the seasonal AR1 process. So I'm dropping in the coefficients. Notice that this is the representation of a regular, how I would write this out if I took that original equation and I wrote out what the autoregressive model is without it being seasonal. I'm just saying, hey, give me 0 coefficients for 1 through 11, and then put 0.9 for the 12th one. And so then this is not explicitly saying it's seasonal, but we're making that way manually. All right, and so now I'm using the ARIMA ACF function. So this computes, the ACF for any process I want to give it. And here we're computing the PACF by using PACF equals true. And now let's go ahead and plot this. So let's look at the ACF first. We're using the tsplot function in the TSA package. And you can see that it's going along here. Now, something that's important with this is that I put down the lag in multiples of 12. And so I've got 0 in between the decreasing ones. So here I've got 0 ACF, 0 ACF, 0 ACF. These are denoting like the year difference. First year, or 1 year difference, 2 years difference, and so on. Let's do the same thing for the PACF. And when you notice that it cuts off right after the first year, or first year difference, I should say. All right, so and that's consistent with what we talked about a moment ago about identifying what our seasonal model should be. All right, so let's go ahead and just do some pencil and paper work on the first order seasonal moving average model. S is equal to 12. So here, it's a moving average model. So a moment ago we were doing autoregressive. Now we're doing moving average. And so here, this is my process of there's a white noise term, and then the one additional moving average white noise term from a lag of 12. And if I sit down and do the calculations on this by hand, pencil, paper, this is really, really similar to doing it for an MA1 process. And so we'll get these results. Now you'll notice that we're going to get 0 for our covariance, our correlation, when we're not dealing with with multiples of 12. Plus or minus 12 in particular. Once we get past plus or minus 12, it completely cuts off. All right, so let's talk about a multiplicative seasonal autoregressive moving average model. And so this is ARIMA PQ by capital P, capital Q, seasonal aspect with a seasonality of S. All right, so here we can see that we are multiplying the autoregressive. So I've got the seasonal autoregressive multiplying the regular autoregressive. I've got the seasonal moving average multiplying the regular moving average. Now, something to be mindful of is that with these, I could actually change the order because that polynomial aspect of it. So it's not really as strict as it presents it here. So remember, a lot of times when I'm dealing with higher mathematics, order matters. The x of t has to be on the far right. The w sub t has to be on the far right for each portion of the equation. But what happens in here, because of the connection to the polynomial, I can switch the order if I needed to. If that would make my analysis easier when I run through things. Now, the properties of the table above don't apply when we have a regular autoregressive not equal to a constant and a constant value, which we represent with 1, or the moving average component, regular moving average, is not equal to a constant itself. And so we typically see a mixture of non-seasonal autocorrelation and partial autocorrelation behaviors, and the so when I look at regular ACF, regular PACF, seasonal ACF, seasonal PACF, most of the time when I'm actually looking with real data, it's all jumbled up and it's hard to spot what should I actually go with on this. And so this is why it's really important to, first of all, get our transformations done before I'm going to do model fitting, before I identify the degrees of things. It's important that I do my differencing first. So do my regular differencing, do my seasonal differencing, then I start looking at ACF, PACF to try to identify the regular ARIMA processes that I want. And then while I'm looking, I'll try to spot multiples of the seasonal components so that I will know, hey, like if it's 12, if I see something going on with 12, 24, 36, then I'll go, hey, I know that there will be a seasonal aspect to consider for this. And in general, so the authors recommend this. I think it's more fluid than this, but they say try to identify the seasonal component first. All right, so let's run through an example. And so this is going to be a mixed seasonal model. All right, so we want an ARIMA 0, 1, so we have 0 degree autoregressive, so it's not our autoregressive, but it is a moving average degree 1 process. And we want a seasonal autoregressive 1 process. And here we're saying, the seasonality is 1 year. All right, so here, this is our process. So what I want to do, I want to start just figuring out the pencil and paper mathematics of this process. All right, well, the first thing I'm going to do, I want to figure out the variance. Okay, so taking the variance, remember in this presentation, how we're approaching it, to make the math easier for ourselves, we're making the assumption that the population mean is 0. If it's not 0, we just shift up and down after we do our calculations to get what we want. So without loss of generality, for this moment, we assume that my process has a population mean of 0. All right, well, I can square both sides. And when I square the left-hand side, this is going to end up being the variance. And all of this stuff over here, I can use to compute what I want. All right, so when I look through here, I know that under the constant variance assumption, this has to be equal to this. All right, here, this is going to be the variance of my white noise process. Here, it's also going to be the variance of the white noise process. Now, at this step, when I look at W sub t, all of the previous x's are constant values in that moment. Therefore, if I have a constant time with respect to the white noise, that's not going to change the mean at all, because white noise has a mean of 0. So I have something that is a constant for the purpose of this expected value when I look at W sub t. And so its expected value is 0. Therefore, this whole thing is expected value 0. Similarly, the same argument is that we're going to have a constant times our white noise with respect to that moment in time. And so then I'm going to get 0 here. And then I have differing index on the white noise. Therefore, I have expected value of 0. A lot of things cancel out. And now what I'm going to do, I'm just do a little bit of college algebra to simplify this thing. And here I'm going to get my covariance at 0, which is the variance of the process. All right. Now, I want to get covariance overall. And so I'm going to just take the original process I have, multiply everything by x sub t plus h. And then I'm going to go through and start doing some calculations. So once I set this up, I'm taking expected values. And now I'm going to sit through and just, crunch this out. All right, so if I put h equals 1, I get this relationship, which we'll see in another presentation in a moment. If I go h minus 1, which actually makes more sense for the calculation because we're talking about lag. Then I can see that in this calculation, we've got these two values. Well, that's just going to be auto covariance of lag 11 here. Same argument of at time t, that is a constant. Therefore, this w sub t is when it's together, we're going to get a value of 0. And then I'm going to replace the portion I have up here in the expected value with this here. Now I skipped a step on this. The next step would be to distribute my white noise term across all of these. Now, once again, we're playing the same game. This white noise, when we think about this, that's in the past. Therefore, when I match it up with the white noise is independent of that constant value. Okay, so that's going to end up giving me a 0. Here, I've got the same subscript, so I know that this is going to be w squared t minus 1. And then I'm going to, when I distribute to this part, I have two white noise terms of different index. So I know white noise, the product of white noise of two different indices is going to have 0 for my auto covariance. All right. And so then boom, I've got that right there. All right. And so then we see this result there. Now for h greater than 2, for this particular process, things are, once they get past a certain point, the moving average part, the regular old moving average component, no longer has any overlaps in the time series. Therefore, we're going to have a lot of zeros when we do our covariance calculations. And what's left is going to be that seasonal autoregressive aspect. And so we can see that right here. All right, so now this gives me a good general formula to work with. If I work with this a little bit and rewrite this, I realize using this, if I have a multiple of h, I can keep on subtracting 12. So if using that formula, instead of having h, I'm replacing h with 12h here. Well, every time I subtract by 12 on the inside, I multiply by a phi on the outside. Doing this iteratively, we can see that our auto covariance at multiples of 12 are going to be equal to corresponding powers of phi times the variance of the overall process. All right, that's interesting. And then dividing out by the right term to get our auto correlation, we have a very nice clean formula for the auto correlation of this process. Now, remember when I did the work for +1 and -1, and you'll notice when I did that, when h was equal to 1, we had this term with a 13. When h was -1, we ended up getting 11, but otherwise these are really close formulas. Well, if I just sit down and do a little bit more work, I can see that the autocorrelation of 1 off for multiples of 12 are equal to each other because of the overlapping aspect of the moving average. And so in fact, this is what we'll get for the autocorrelation. All right. And this should be on another line. That's a typo. Everywhere else, we have an autocorrelation of 0, except for these few special cases. All right, so let's go ahead and simulate one of these processes. Here, I'm going to say that phi is equal to 0.8. I'm going to say that theta for the moving average is -1/2. All right, so here are the coefficients of phi. So notice that everything is 0 except for the 12th one. Here, I'm going to set up my moving average of -0.5. So this is appearing here effectively. Now I'm running the ARIMA autocorrelation function by just dropping in the values. And now let's go ahead and get the values for it. So here I'm going to see the autocorrelation function. All right, and notice I have a lot of zeros in here. I have the huge spikes at multiples of 12, but plus or minus 12, we can see that they're equal to each other, and they're negative in the opposite, or they're negative pointed in the opposite direction. If we look at the PACF, notice that we have a spike at 1 seasonal aspect, and then it kind of trails off. All right, now seasonal persistence. Seasonal persistence occurs when the process is nearly periodic in the season. All right, so for example, the average monthly temperature over years, each January is approximately the same on average. Each February is approximately the same, each year over the average of the entire month, and so on. And so what we're going to do, we're going to model this as x of t is equal to the seasonal component that varies according to a random walk plus white noise. And so here, my seasonal component is going to be the last value of the seasonal component, so from a year ago, plus that random walk aspect. Now, something that's important about this particular model is that we're going to say that these two white noise aspects that we have are uncorrelated with each other. And so a process of this form will have a large ACF that will decay slowly at multiples of the seasonal aspects. And if I want to, I can go through, and if I do the differencing off of this, if I just do the little bit of college algebra on these equations, we'll see that this is in fact V sub t plus the difference on the current white noise and lag from last year's white noise. All right, so now the next thing we want to talk about is seasonal differencing of order D. All right, so seasonal differencing is indicated when the ACF decays slowly at multiples of the season length. So now, when I'm doing this in real life, I need to know what is the length of a season. All right, so if it's a year or a quarter or a month or something, that it would make sense for me to know that going into my project. Now, when we do this, when we're trying to spot this, we need to have negligible ACF between the seasonal aspects. And so here's how we'll write out seasonal differencing of degree D. Usually in most real-life processes, differencing of degree 1 is sufficient. All right, so now here is the mamma jamma big equation for the multiplicative seasonal autoregressive integrated moving average model, or SARIMA. All right, so a SARIMA model, we'll write that as ARIMA PDQ cross PDQ, all caps, and subscript the season aspect. And so I already talked about this a moment ago, but I'll repeat it to make sure we get it. Here's my seasonal autoregressive. Here is my seasonal moving average. Here is my ordinary autoregressive. Here's my ordinary moving average. Here is seasonal differencing. Here is ordinary differencing. Here is my regular old time series. So the left-hand side corresponds to the autoregressive. Here I have the white noise portion for the moving average. And then this shift up and down addresses the overall population average. So once again, W sub t is my Gaussian white noise. So in this model, we're saying that it has to be Gaussian for this point, from our point of view. We're no longer just allowing a wider range of moving average for this. Now, something to notice is that because we're forming all of the operators on our backshift operators as polynomials, the order of these actually doesn't matter off of these. That's just, an algebraic fact. the order of these two don't actually matter. All right, so let's go ahead and run through an example. So let's consider an ARIMA 011 and seasonal 01112 process, so that 2 should be subscripted. All right, so this is a seasonal non-stationary process. All right, so here I'm differencing in the regular manner. I'm differencing in the seasonal manner. I have moving average degree 1. I have seasonal moving average degree 1. And so we can write out the equation this way. All right, so now I'm going to rewrite the differencing as a polynomial on the backshift operator. And I'll write out the moving average portion as a polynomial on the backshift operator. Now, when I get to this point, as I'm working through this, remember that if I have a common divisor on the left and the right-hand side in terms of the backshift operator, I probably want to reduce things down as appropriate. And so then, like, let's say I'm looking at this and I noticed just by working through this that I had, let's say, a common factor on left-hand side, common factor to the right-hand side. I would want to divide out that common factor to both sides, then go back and adjust what my model is to figure out what's going on. So I would have to do some work. Wherever those factors are coming from, left and right, that's probably where I would remove them. But it is possible, off of the algebraic structure of just regular old polynomials, that it may be that I can move around degrees and get maybe an easier to understand model. So I would want to take the time to work through that. All right, so the multiplicative model assumption seems to work well with many seasonal time series data while reducing the number of parameters that must be estimated. And so here you'll notice that there I could represent the right-hand side as moving average degree 13, but you'll notice that instead I have the same parameter twice for each of these, and they're being multiplied out. And so what that does is, in fact, if I fit, theta and capital theta, I don't have to fit this value at all. And so that's a lower degree, means that I really actually need less data to fit this. Selecting the appropriate model can be really difficult. So as a general guide, start with your transformations. Then, so like log transformation, square root transformation, like if so let's say I'm in a situation I don't have constant variance, then I would probably use a log transformation. If I have count data, square root transform tends to solve problems with that also. After I do that, I'm going to start differencing until it looks like to me that I have a stationary time series. So remember, constant population value and constant variance with respect to time. All right, then I would use ACF and PCF to simultaneously identify the degrees of regular ARMA and then seasonal ARMA. For the seasonal ARMA, I have to know what a season length is, and then I need to kind of spot that as I work through the process here. All right, so let's go ahead and run through an example. This is from the textbook. They're taking a package in base R, the air passengers data set, which is from 1949 to 1960. This is a classic data set from Box and Jenkins, and this gives the monthly totals of international airline passengers. And so here, this is in the data sets package. This automatically loads when you open up R, unless you tinkered with your settings. All right, so what we're going to do is we're going to look at our data and we reach a conclusion that I need to do something. So first and foremost, I'm going to look at it. I'm going to go, wow, I don't have. So if I look at this plot, I see two things. I see a trend and I see increasing variance as I go from left to right. All right, increasing variance. Typically, we're going to use a log transform. So I'm going to go and do a log transform. I go and I do a log transform. I go, wow, I still have a trend. I need to detrend this. I'm going to use differencing. Now I look at this and I realize that I probably have a seasonal component. And, travel in the United States is definitely going to be going along a yearly cycle. So I'm going to do differencing or seasonal differencing with a season of 12 since I've got months. And so all that work here is done this way. And so here I'm doing that log transform. I'm taking the difference of the log transform, and now I'm taking the seasonal difference. Notice I've got a lag of 12. That's important. And then I'm plotting everything that I just showed you. So in real life, I would look at one plot, do the transformation, do a transformation, do a plot, do a transformation, do a plot. Do this until I feel like I don't have anything else to transform. And so now I look at this and I go, okay, yes, I have that looks stationary to me. I do not see a seasonal trend. All right, so now let's go ahead and just run through the month plots. That's in base R, just to see what's going on. If I do a month plot, so here this is each year for the January data, February data, March, April, May, and so on. And so we clearly see a trend, going from left to right with respect to each month. So now here is it after I do the log transform. Oh, that doesn't really fix anything. All right, now when I take the differencing of the logs, notice that we've got kind of this, smoothness going on there. When I do the differencing, okay, now things start looking, more random in relation to the average of each month. And when I do the seasonal differencing, so now I did consecutive differencing and seasonal differencing. Now everything looks random with respect to their respective month. And so now let's go ahead and look at the ACF and PACF. All right, so the ACF seasonal lag cuts off at 12. That's pretty clear on this one. So the seasonal, I've got 1 and then nothing, nothing, nothing for seasonal lag. Then when I look at the PACF, all right, so I might have 1 here and then nothing, nothing, nothing for seasonal PACF. For regular ACF and PACF, it's not so clear to me. So I see that I've got a value here. I've got a value here sticking up. And so possibly maybe a low degree. So like here, degree 1, possibly degree 1 might be worth considering. I've got this sticking up. So maybe I would try degree 3, maybe. I'm honestly not too sure. So what I would be doing, I would be, exploring multiple models. The authors went through just a few, and we'll take a look at those few right now. All right, so the authors chose autoregressive 1, moving average 1, and then moving average 1 on the seasonal aspect, and we fit it. And we can see the ACF of our residuals and whatnot. Now, a lot of these look pretty close. And when I went through and I was preparing for this, I was looking at the ACF and the the AIC and the BIC to decide what's best. And so here is the AIC, the corrected AIC, and the BIC. Now here we're going to drop the autoregressive. We got moving average, moving average. We've got our plots. Things look, to my eyes, relatively close to what we had before. Here is our AIC, corrected AIC, and our our regular BIC. And now we're going to go with an autoregressive and seasonal moving average, both degree 1. To me, the plots still look in the same realm of each other. And we get our AIC, corrected AIC, regular old BIC. You know, I forgot to show it in here. But what I did with this was I took, I extracted each of these values like when I was preparing, and I saw that the model that the author ultimately picked had the best AIC. And so that makes sense. So this is the one to go with. And so here is a forecast using that model. So it looks like the forecast is at least consistent with what we had before. And so here we can get our predicted values. All right, that's all I've got for you. Life is short, do math.